Welcome back, everybody. And off we go. Do we have any suggestions for our next segment? We are currently waiting for suggestions for our next segment.
I don't know if somebody else has anything to ask because I've been asking like most of them.
That's okay.
So that's fine. They can go.
You've been a fine leader this whole semester. No need to stop. But if somebody else does have a question, do not hesitate to jump on in. Looks like that's your turn again, Hassan.
Okay, so for like the same test, if you go up a bit.
Oh, sure.
So,
let me try to find it. Okay, I got multiple windows open and now I'm paying the price. Here it is. Okay, go up a bit to Lewis.
Yeah, there. So like to do the stable Lewis structures and then off of that and then indicate each bond and then the geometry for them. Can we do one for practice?
Do you want to do the whole deal or start at 2B or it's up to you?
Can we do the whole thing?
The whole thing. Why not? We've got time. All right. Moving on over here. And back here. Nope. Go. Okay. So we're going to do this one. Hydrogen tellurate, but you don't need to know the name. And it's an anion. So we got to count up valence electrons first. Hydrogen group 1. Tellurium under sulfur. Tellurium under selenium under sulfur under oxygen, group 6. 4 oxygens, each with 6 carbons. 6 carbons. 6 valence electrons. And an anion has an extra valence electron. And 5 times 6 is 32. 5 times 6 is 30 plus 2 on the ends. So 32 electrons when we're done. Central atom tellurium. Please don't attach hydrogen to tellurium. This is an oxy acid. There's a reason why they show up on every test almost, because they're very important. Next test, we're going to start talking about acids and bases. I need to get you ready. Okay, so the skeleton's like that, and an oxy acid always has the hydrogens listed in front attached to an oxygen, each one of them, and there's only one here. You pick one of those. Now it's time for some bookkeeping. You got to come up with 32 electrons, and you've drawn how many bonds? 5? 1, 2, 3, 4, 5. How many electrons are in 5 bonds? You guessed it, 10. 22 more to go. Lone pairs until octets are full. 6, 8, 12. Did I do some bad math just a second ago? It seems like I'm coming up with too many electrons. 6 times 4. Group 6 times 4 is 24. 32, correct? Have we come up with 32 yet? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay, I was miscounting when I was doing it. We've got 32, so we're done, right? No, we're not. We're not done. Formal charges say we've still got work to do. I'm going to copy that before I move on. Formal charges say each oxygen with 3 lone pairs is an anion. You get 3 anions and 1 tellurium. And why is the tellurium plus 2? Because Tellurium, the atom on the periodic table, has 6 valence electrons. That's why we used the 6 here. And here it's sharing 8, which is like owning 4. So it's too short of the amount of electrons it owns on the periodic table. You can get this to be way better. 2+ is like, oh my God, you made a huge mistake. If you have any 2s on any charges, you're not done. Okay, so we can get rid of both those 2s and 2 of the minuses by taking electrons off of the oxygens that are anions. And you pick any 2. Why don't we pick a huge eraser? Pick the bottom one and the top one and put them back on. You just took off 4 electrons. You know that, right? You better put them back on or else you have the wrong number of electrons. I'm putting 2 back here as a pi and 2 here as another pi. And the only charge remaining is this one here. And you've only got 1 charge where you had 4 before. And one of them was a 2, which was awful. You're finally done. And then you show this to Dr. Yakel and she says, oh my God, it's not right. You're not finished. You forgot to put the square bracket in the charge. And I say, sorry, Dr. Yakel, Dr. Whitaker says it's okay when you do all the formal charges. You clearly know it's an ion, and you're even telling me where the anion is. With those square brackets, it just puts the charge outside the brackets, and you don't even know which atom has the formal charge. So you don't need square brackets in this course for charged species. So 2A is done. Moving on to 2B. We don't do a valence electron count for organic molecules. We just go by the nature of the atoms found in organic chemistry. Very popular ones, C's, H's, O's, and N's. And we're going to just do it. Where's a good spot to do it? Right beside it? Why not? So Lewis structure, you've got to show all the bonds. So the molecule starts. First of all, before we start, find patterns that our functional groups we're supposed to recognize. We're supposed to recognize when you go CO2, then another C, that the CO2 is either a carboxylic acid or in this case, a carboxylic ester because it's attached to a carbon. And there's only one way to draw a carboxylic ester. Carbonyl. The ester is to the left because the O was to the left of the carbonyl. Oxygen needs 2 bonds, 2 lone pairs. And now you can connect the CH3 to that O. That's an H. I made it worse. Okay, and you've covered the CH3 in green, the O of the ester in blue, the carbonyl of the ester in blue also, carrying on to a carbon with 1 H. The carbon with the H also has sticking off of the chain an NH2. What's the nature of nitrogen? Well, we've got the bond part of its nature done, 3 bonds. And what's the lone pair part of nitrogen's nature? 1 lone pair. Okay, so that's sticking off the ring. That's why it's in a ring. Sticking off the chain. That's why it's in a parenthesis. And then the chain continues from this C to the next C, which is void of hydrogens. There are no hydrogens on this C. There are no hydrogens on the next C. The next C has 2 hydrogens. Don't worry about carbon's octets until you're finished this exercise. We're at CH2. We're going to a C with an O and a C. I'm going to do it the wrong way first and then show you why it's wrong. It's in red. It's going to be wrong. C, you're reading it across and you see CO, CH. And then you see a CH2. We're going to be erasing all of this. It's a disaster. I want you to try to fill this carbon's octet right now. You're not allowed lone pairs. It's a fact. This one we'll be able to take care of later. We will. Let's finish this disaster portion here. The only way to get this carbon, the way you chose to draw it, the incorrect way, is to put a triple bond. Now your carbon's octet is full and your oxygen octet is full, but your oxygen is 2+. There's where you've got a huge problem. This species is uncharged. You made a mistake. Start over. The other option, when O is written like that in the middle of what seems to be a string, is carbonyl. It's still red, but this time it's not a mistake. And now you'll be able to fill octets and not have charges. C with an H, C with two H's. Filling in the octets, we'll do our pi bonds in baby blue. This carbon doesn't have a full octet. You have two choices of pi bonds. One's a good choice, one's bad. Can you make a pi to the left? Answer, no. If you go to the left, this carbon now has 5 bonds, and an octet violation, you're not allowed that. Go to the right with a pi bond. Now this carbon is closer to having a full octet. You can't go to the left for the same reason as before. You got to go to the right again, and you just filled the octet for both carbons. It's called a triple bond, which is really a sigma and 2 pi. Going over here, don't put a pi to the left. Got to go to the right, and you're done. There is your Lewis structure for this molecule. That is the answer for 2B. 2B.
But he said the most stable structure. Is this the most stable?
This is by far the most stable structure. Any other structure is going to lose at least a point. You'll lose multiple. If you did that O in the middle like before, that isn't the right molecule. You're going to lose more than a point.
No, we don't need to draw any wedges or dashes?
No, on this question, you will not be drawing wedges or dashes. I do not want to know about tetrahedra and stuff like that. Okay. You'll tell me about tetrahedron when you do the geometry, but